So in total, we had 468 participants who completed the online survey, and these came from 23 different countries. However, about 90% of participants came from approximately 6 countries, and we can see that in the top left pie chart here, with most of the participants coming from either the UK or China. We had both an English and Chinese version of the survey because we're quite interested in seeing if people behave differently in different countries. We had about 61% of participants were male, and just under a half were aged between 18 and 30. And this means that the majority of participants were aged above 30 years old. Looking at the BMI, we can see that just over half of participants were normal in weight, and the remaining half were either overweight or underweight. We can see from the occupations of the participants that almost 3/4 had some occupation other than being a student in the fire safety profession or the lift profession. And this is important because it shows that the participants who completed this survey were not just from a narrowly a narrow occupation type, like all being students or all within one business. They're from a variety of different occupational backgrounds. We can also see that some 63% of participants have a lift in their place of work or study. Okay, so we've collected this data to quantify various types of behaviour of pedestrians on and around lifts and escalators. Now we're going to talk a bit about the models we've developed based on the data we've collected. With regards to escalators, we've developed a model within Building Exodus which can, in addition to representing the types of behaviour on the escalator, like whether an agent will choose to walk or ride, the side which they'll use on the escalator, we've also developed 3 different choice algorithms which simulated people within the software can use to determine which device they will use, whether they use an escalator or stair or any combination of the two. The first method is a proportional system whereby agents elect to use a device based on user-specified probabilities. So a user might specify an agent has 70% chance of using an escalator, and in the simulation 70% of agents will elect to use the escalator. The second method allows agents to think for themselves, and agents will select a device based on their shortest perceived time. They'll elect to use a device which they think will allow them to traverse the area in the shortest perceived time. And agents not only consider the travel speed and distance, but they also consider the number of people queuing for each device. The third method is a hybrid of the other 2 methods, and this allows agents to adapt to the levels of congestion in the catchment area of the escalator or stair. Okay, so here we have a virtual reality representation of the model where there's 3 escalators, 1 going down, 2 going up, and a staircase. And what we can see is if we look at the escalator going down, we notice some people are riding, some people are walking on the escalator, and gradually a queue begins to build for the escalator. And what we notice is that as the queue builds, agents begin to adapt and say, I'm not going to wait for the escalator. I'm not going to wait for the queue up for the escalator. I'm going to use the stairs instead. With regards to the lift model within Building Exodus, we've developed the capacity for a user to define the various physical characteristics of a lift. These include the dimensions, the number of people that can fit inside the lift, and the shaft. A user can specify the kinematics attributes of the lift, like the acceleration, the jerk, the maximum velocity, various delay times associated with the lift, and there's also a lift car control mechanism which allows a user to define what floors a lift will service during an evacuation. We're also working on a dispatch algorithm module where a user can define their own floor dispatch algorithm for a lift. We've also developed a simplistic agent model which controls how people behave within the simulation. There are essentially 3 types of behaviour associated with this. The first is the lift selection method, whereby agents decide whether they're going to use the stairs or lift. There's the lift wait location method, whereby if an agent chooses to use a lift and they enter into a lift waiting area, they have to decide where they're going to wait within the lift waiting area. And there's also the agent open lift selection method, whereby when a lift opens on a given floor, which agents decide to use the lift. In addition to the simplistic agent model, we've also developed a more advanced agent model which can incorporate the data we've collected. This includes all the features of the simplistic agent model with the addition of a lift selection query assignment engine, and this basically allows a user to not only define agents who will use perhaps their closest lift or closest stair, but they can define probabilities of agents using a lift based on their personal characteristics. So you can define agents who are on given floors with a given body mass index having a given probability that they'll use a lift or a stair to evacuate. We've also got a lift wait area congestion redirection, whereby agents have a congestion threshold. When they enter into a lift waiting area, if the average levels of congestion are above the congestion threshold, then they will redirect to use the stairs. There's also the lift wait time behaviour, where agents won't wait indefinitely for a lift during an evacuation. They'll wait a predefined amount of time before they redirect. Again, this is based on a distribution. Okay, here we can see an example of the developed model. Here we've got a simple 10-storey building with 4 lift cores, and the top 3 floors are populated with 160 people on each floor. People here are represented as in congestion mode, so you can see them more easily. And what you're seeing here is that floor 9 is evacuated very quickly, and floor 8 is evacuated after. However, some people begin to redirect to use the stairs because they're not prepared to wait any longer. You can see people are evacuated from the top of the building to the bottom, where they evacuate to the exit. Okay, so now we've collected our data, we've developed a model. Now we actually have to use the model to explore the impact of different types of human behaviour on operational strategies with regards to escalators and lift during evacuations.